Hi all. This is the short story, or maybe the long story, of a eutrophic Danish lake. The lake has been formed during the last glaciation, like many other Danish lakes, and it has received untreated wastewaters as long as there has been people around the lake, which is really many hundred years. So that means that the lake has also been heavily polluted. So in the early 90s, the professor at Freshwater Biological Laboratory, he concluded that the lake was in a very poor condition and that the plants at the bottom has vanished. The lake is actually a bog from the beginning. It has been dammed when they built the castle in the 1200th century. So it's now 2 meters above the normal water level. And over all these hundreds and hundreds of years, it has received wastewater. So that means that the accumulation of organic material in the bottom are quite substantial. The catchment is quite small. And if you look at this picture here, you can see that there's still some forest and nature around it, but this is something we will call semi-nature because it's within a landscape with people in. In order to understand the long history of the lake, we can take sediment cores, and that's what you see on these pictures here. Sediment cores was taken in the middle of the lake and pulled up in order to study what was left of remains in the sediment. We aim to take a very long history, but as you can see from this picture here, these are each of the cores that was taken subsequently through the sediment. You can see the sediment layer over here. We only reach back to 1606. And what we are looking for in the sediment is remains from different organisms, like these that you see here. So one, for example, is diatoms and chironomid head capsules. They persist in the lake, and we can take them up, and then we can study and see how much of it is left from different times. And that's what you see on these time series here. If we put this together, then we can reconstruct the phosphorus levels, and that's what you see here. So this is, if you go down here, this is age, and this is what the phosphorus levels is in modern time, because there we have measured it. But if we look at what it has been over time, so now you have the whole history here, you can actually see that the phosphorus levels that we have now are not that different from what we had long back in time. So actually it was quite high here also in the old days. And that of course come from all the wastewater that was entering the lake. So we can conclude the lake has been eutrophic for a very long time. So with that, it also comes that it has low second depth, no macrophytes, heavy algal blooms, oxygen depletion, a skewed fish population, and with that also small zooplankton species. So we can ask what to do about it if we want to restore the lake. Well, one obvious thing is to remove the fish. These are top predators. So if we remove them, they might make better conditions for the zooplankton. So in the 60s, the wastewater was stopped. So it was not stopped, but it was treated well. And over the coming years, up to the 70s, the P phosphorus removal was included. And then in 85, a biomanipulation took place. That was to remove the amount of fish, especially the planktivorous fish. And that happened right here. So the planktivorous fish was removed, but as you can see in the coming years, there's still a high amount of fish biomass in the lake. So if we study the composition of the fish biomass in this year here, 2004, which is some years after or a long time after the fish manipulation, then we can see, especially here, that these are roach, that they were still had a very high abundance. So you can do the biomanipulation, but the biomass of the fish that takes the zooplankton will soon increase again, and then you are back to the same conditions as you had before. An enclosure experiment can show the role of the fish. So this is an experiment we have made in the lake, where we had big enclosures like these ones here. They were 5 meters in diameter, in a water depth of 3 meters. We added a roach to 3 of them and kept 3 others free of roach. And then we did over 6 months measure the basic conditions in the lake, as well as phytoplankton and zooplankton abundances. So here you can see that our enclosure system is right here in the lake. And what came out of that? Well, if we look at it from an general perspective, you can see here the difference with fish. These are the gray ones, and without fish is the white ones for phytoplankton, picoalgae, bacteria, flagellates, microzooplankton, and macrozooplankton. We can see differences. We can see a doubling in the zooplankton biomass if the fish is removed. Therefore, we can also see an increase in the individual zooplankton body size because they are not eaten by a fish, an increased grazing pressure on the phytoplankton, and therefore a 2/3 reduction in the phytoplankton biomass in the case without fish. So they have a very strong effect. We did also study a lot of other things. They come here. I won't go through them, but we did study water chemistry. We did study bacteria and flagellates, and also zooplankton and phytoplankton species composition. You can read all about it in this paper if you're interested. Another thing that's interesting about the lake is that zooplankton can use the macrophyte as a refuge. So we have made some other experiments. We have a study how much does the macrophytes mean for zooplankton for hiding. And this is shown here. So this is dates over summer, and these are numbers of cladocerans per liter. And here you have three different situations. This is the open water in the middle of the lake. And these two other ones here are in between plants, different types of plants, reeds and polygonum. So and please note that this is a logarithmic scale. So there are 10 to 1,000 times more zooplankton if you have plant beds in the lake. So that's very important to have. So that could be another way of supporting the zooplankton if we could get the plants back. We have made a new restoration strategy in the 2005 that included aluminum treatment and biomanipulation again. And the biomanipulation you can see here, this is the number of fish that has been removed. This is bream, this is roach, and these are other different fish species. In total, almost 6,000 tons, 6,000 kilos of fish was removed from the lake. And then the lakes was treated with aluminum. So aluminum chloride will bind to all particles and to the molecules, nutrient molecules, and then drag it down to the bottom. And that's what you see here. So this is the total phosphorus in the epilimnion in the years before we did the manipulation. So this is here. So it increased severely during summer, and this is from where the treatment was made. So here, where the aluminum was added, then we have a substantial reduction of the phosphorus, and it was all brought down to the sediment. And these two ones here, this is the 2 years after the treatment. So at least here it had some effect that there was a reduced level or reduced concentration of phosphorus after the treatment. But did it last? Well, not really, because if you look at this one here, this is TP before, 1 year after, 4 years after, and 7 years after. When we come back 7 years after, we are actually here where we started. And that, of course, is the same for the second depth. The second depth was 0.8 before, and it actually went up to 1.4 in the few years after the treatment, but given back. So therefore, the transparency was improved maybe in the beginning, but it did not really last. But here, if you look at this, this is the second depth over years, over long time series here, where you can see the bad conditions here, where we have 0.5 meter of second depth. Then it improves just after we have had the addition, but then it goes down again. Now, if we look at the chlorophyll, which comes here, so this is a mean chlorophyll. So it's an interesting thing because despite the fact that the chlorophyll level, the phosphorus level was still high, we did not have so much chlorophyll. So if you look at this one here, you can actually see that in this area here, so this one should go down here. So it's to show that we have to have very little chlorophyll levels, despite the fact that we have a high phosphorus. So what can cause a reduction in chlorophyll while we still have a an increase in transparency? So this might be related to other factors, and one could be the zebra mussels. So the sena, like we have talked about for Esrumsø, is also present in this lake. So they can filter a lot of water. So they can filter up to 1 liter of water, but how many mussels will it take to filter the whole water? We have studied the mussels, and we can see that there's actually quite many mussels, at least some years in the lake. So that might be a biological component that actually can control the water in the lake. So what they do is that they will feed on all the particulate material. They will make fecal pellets that will sink to the bottom, and therefore we will have some of the phosphorus and some of the particles immobilized in the sediment. So from a management point of view, what will it take to improve the water quality in this lake? Well, we can look at all the things like reducing fish, adding mussels. We can also look into the nutrients. So how can we reduce the nutrient input to the lake? The nutrients are no longer actually coming from outside, but it's internally in the lake. In the sediment, there's a lot of nutrients. How can they be restored back? And then we could also look at the macrophytes. So would it be possible to use macrophytes for a restoration plan? So all these things, including the fish, could be part of a restoration plan for this lake. And that's what we want you to try to think about and come up with a good suggestion for.